A light wave is just like any other kind of wave. I'm sure you've seen this diagram before. We should remember that a peak to peak is going to be a wavelength, and then from the middle point up here to the top is going to be our amplitude. And light is interesting because it displays a spectrum of colors. So we have basically the Roy G Biv. The left side is going to be the red light, the right side is going to be the blue light, but the wavelength is going to change as well. So it's going to be really long towards the left, and then it starts becoming really frequent towards that blue light. So basically we could say that this is going to be a long wavelength, and this is going to be a low frequency. And on this side, this is going to be a short wavelength and a high frequency. So the red light and the blue light. In general, there's two ways that waves can combine together. They superimpose on top of each other, and it's called interference. And one is the destructive method. So it's like a crisscross pattern, like this. They're basically kind of canceling each other out in a way. So this is called destructive interference. And so the light's getting dimmer. And so you'll basically kind of subtract the two amplitudes, but it's a little bit more complicated than that. Now, there's another way you could do this, which is the kind of stacking it together like this. So increasing the peak sizes. And this is called constructive interference. And this is making the light brighter. So you would basically add the two amplitudes. Again, it's a little bit more complicated than that, but in general. You may have heard of the two-slit experiment. They're basically testing the diffraction pattern of photons and electrons. So you can imagine taking some rocks and throwing it against a wall that might have two slits in it. Well, if you sort of take a look at the pattern that would form on the wall behind it over here, you'd notice that those rocks just land in two spaces. Now let's say we sent some waves towards the same two slits. What would happen is once they reach those two spots, they're going to interfere with each other. They'll come out each side, and they'll create like a little striped pattern on the wall over here. Now, what's interesting is that you can do this with both electrons and photons. So you send it at these two slits, and the funny thing is if you're not watching it, if you just let the experiment run by itself, this pattern will form. You'll get a little striped shape, and you'll be like, oh, well, that's weird. Which hole are they going through? Like, how is this happening? How are they interfering with each other? But if you start putting a camera here and you start watching it and you start testing, okay, which hole does the electron actually go through? Which hole does the photon really go through? And what happens is that effect goes away, and they just go through whatever hole they're in. You can get two marks. So depending on whether you're watching it or not watching it, you basically get this thing called the wave-particle duality. So particles are acting both like particles and waves, photons and electrons. So this is really interesting. These observations kind of lead us to some interesting equations. We could say, let's take a beam of light. We'll take the energy of the beam of light and divide it by the energy of a single photon, and that will give us the number of photons that are in that beam, and that kind of makes sense. Let's remember that the energy of a photon is always positive. Well, that's pretty important. We discovered the energy of a photon based off of black body radiation. You can see from the spectrum that as you go towards the blue light, the frequency increases, and yet the light becomes dimmer and darker. And so even though there's a dim, dark light, there's a high frequency, and so they're able to come up with this equation right here. Energy of a photon equals HF. So as the frequency increases, the energy increases. And we also know that C equals the wavelength times the frequency. So you can kind of rewrite this equation as HC divided by lambda. And so now we have two different equations that we could represent the energy of a photon, and that's what help us for that equation. Well, what about for any other particle, not just a photon? Let's just take Einstein's famous equation equals mc squared, and let's take the mc squared portion. Let's set that equal to this thing over here, hc over lambda. We'll see that the c's will cancel out, and we'll be able to restructure this and find the de Broglie wavelength, which will work for any particle besides the photon, because you notice it'd be h divided by the momentum, and since the mass of a photon is 0, it's not, you can't divide by 0. But the idea is that this will work for other particles. You'll be able to figure out the wavelength of anything in the world, to be honest, because everything has a momentum. In order to solve these equations, you might need to know some constants. So let's consider the speed of sound first. So that's going to be 340 meters per second. We'll compare that to the speed of light, which is going to be 300 million meters per second. It's a bit faster. But now that we know the speed of light, we can actually find the wavelength and the frequency of any one of these. If we know the wavelength or the frequency, we could figure out all the other ones. Frequency is just going to be hertz, and that is 1 over seconds, where seconds is in the denominator. We also have this thing called the wave number, which is equal to 1 divided by the wavelength. This usually represents it in radians divided by meters. Let's not forget Planck's constant, which is h, super important at 6.626 e to the negative 34. But in this context, we should probably represent it as kilograms, meters squared over seconds, because these three things are going to be factors in all these equations, so we want to make sure the units are actually correct. Let's categorize the type of wavelengths that you might encounter, but let's not forget to convert to meters most of the time. So we're going to try like the gamma rays and the X-rays and the UV rays, the visible light, infrared light, microwaves, and radio waves. Well, the gamma rays have a very small wavelength, so less than a picometer. This is extremely small, so really high energy, high frequency. So do the X-rays. They're around picometers to nanometers. Once you get to the UV rays, it starts becoming a little safer, 100 to 400 nanometers. From 400 to 700 nanometers, probably the most important number to remember, this is the visible light spectrum. We have our infrared starting at 700 nanometers, going up to 1 millimeter. The microwave is from the millimeter up to the meter, and the radio waves are actually really long wavelengths, so they're bigger than a meter, and that means they have very low energy, so they're super safe. Everything in the universe absorbs or emits light at particular wavelengths. You might find that some are going to be stronger than others. We'll call them strongest wavelengths. You might find a specific peak, maybe 2 peaks or 3 peaks of these particular wavelengths. This is going to create a unique atomic spectra for each substance or each element, and it's going to basically give you which colors you'll see being emitted or absorbed by this particular substance. If we were to calculate the peak wavelength of blackbody radiation towards the blue light spectrum, we'd be able to use the wave peak is equal to the Wien displacement constant, which is 2.898 e to the negative third, and this is in units of meters, and then times the Kelvin temperature. So just make sure when we divide this by the temperature that is in units of Kelvin, so that way we can find the wavelength on top. And this is Wien's displacement constant. At some point, Einstein started working on the photoelectric effect, and he noticed that when you shine a light wave towards the surface of a metal, a little electron will start popping out. So this is electron ejection from the surface of this metal. And we can kind of consider the total energy of an electron to be kinetic energy plus this binding energy. The binding energy, this is what's holding the electron in place. If you can reach that particular energy with a light wave, and the light wave hits that and reaches that specific amount of binding energy, this is called the threshold frequency. If it can reach that amount and sort of over-deliver, the rest of it's going to be kinetic energy, and that electron will escape. We can calculate the kinetic energy of this electron in 2 ways. We can use HF minus binding energy, or we can use the regular old 1/2 mv squared, because this is just a regular old electron. But this is the non-relativistic version of this equation, so should be a little more complicated once that electron starts reaching the speed of light. but in normal situations, this will be just fine. Usually when we think of an atom, we think about a little nucleus here that might be positively charged, and then we kind of imagine some electrons that are sort of orbiting around this nucleus. And as we start to get further and further out, these rings will actually start to become thinner and thinner. We'll go over the real shapes of atoms later, but for now we'll stick to this design, and we'll just say, label these 1, 2, 3. And let's say we could go from n equals 1, n equals 2, n equals 3, n equals 4. These will correspond to which layer, which level it is. And this is where we kind of get our sublevel shapes. So we would have the 1s sublevel over here. In the 2s, we would actually get 2s, 2p. Once you hit the 3, you'll have 3s, 3p, 3d, and the fourth one is going to be 4s, 4p, 4d, 4f, and then it'll only be these 4 as you keep adding on more n's. We should also be able to label these energies, so we'll go E4, E3, E2, E1, and as the electron sort of shifts from the higher levels closer to the nucleus, it will experience a negative delta E. It'll basically lose energy towards the lower potential. This is when we have not minus n, but as it starts to go further out, it will absorb the energy, so it gets a plus delta E, and this is when the n's actually get bigger. This is pretty important. This is how the absorption and emission works for the electron's energy. This delta E occurs when energy is emitted or absorbed from that electron when it transitions plus or minus to n levels. Now let's take this from the perspective of the electron. That's what's actually gaining or losing that energy. So it's negative energy when it's emitting, and that is when it goes minus n levels. Or it's positive when it's absorbed the energy of the light, and when that goes plus n in the levels. We can calculate the delta E of any atom as long as we know the energy of the final energy level and the initial energy level. This is going to be for any atom. But it's sometimes difficult to figure out what those energies are, so usually we have to make approximations or usually just study hydrogen. Well, let's consider hydrogen or single electron ions like helium plus, lithium 2 plus, beryllium 3 plus. What's interesting about these is that they have degenerate orbitals. So if you look at this n right here, if you got the same n, you end up having the same energy because you only have a single electron. So if you manage to put that electron in this fourth energy level, it doesn't matter whether it's in any one of those, it'll all have the same energy. This only happens for hydrogen and single electron ions. But because of this, we can actually even calculate the energy of that nth level by setting E sub n. It's going to be negative 2.18 e to the negative 18 joules, and then we'll take our 1 divided by n squared. And we also want to consider the z squared. That's going to be the atomic number. So the atomic number references the number of protons that are in the nucleus, and so therefore z is really referring to the nuclear charge. So it's just basically taking that into consideration to calculate the energy of that energy level. While this equation worked for any atom, this equation and also the Rydberg equation only work for hydrogen or single electron ions. The Rydberg equation, here's the constant, that would be 1 over the wavelength equals, here's our z squared again. We could use the Rydberg constant and we'll multiply that by 1 over the NL, that's going to be the smallest energy level, the smaller one, and then subtract that by 1 over NG, that's going to be the greater energy level. So like this would be 5 and that would be 2 if you were going from the fifth to the second or something. So you'd use this to figure out the wavelength, you use this to figure out the energy of the hydrogen or single electron ions. That Z is going to be the nuclear charge right there. So far we've seen the damaging effects of light. If you give something too much light or too much energy, the electrons will be ejected from the surface of that object. This will happen for anything. If you give the exact amount, correct wavelength, the correct frequency, then the electrons will jump around and you'll start actually seeing colors. So I guess that's what's causing all the colors happening around us. But if you don't give the right amount, the not correct amount, is not particularly the exact amount for the causing the jump, it's not a right number, it's the wrong number, then nothing happens. It's not even going to be absorbed. And of course, all these things are going to be probabilistic. So like, sometimes they happen and sometimes they just don't. So that's just the nature of quantum mechanics, I suppose. There's certainly a lot of uncertainty in quantum mechanics, and one of those things is this thing called complementary properties. Complementary properties. Those are properties that cannot be measured simultaneously. This would be things like position and momentum. We can't measure those two things at the same time. Time and energy. Like, you can't hone in on a specific moment in time and calculate the energy at that moment. Angular position and angular momentum, which is going to be, of course, the angular version of position and momentum. And we could also not figure out from the phase of a light wave, we can't figure out which phase we're in and figure out the number of photons. So those are some complementary properties. You can't measure both of those things at the same time. Heisenberg's uncertainty principle is going to be basically just for this thing, the position and the momentum. We're going to say that the uncertainty in the position of x times the mass times the uncertainty in the velocity is going to be greater than or equal to Planck's constant divided by 4 pi. These are uncertainties. Uncertainty. These aren't like change of x and change of velocity. This is the uncertainty. And well, that's Heisenberg's uncertainty principle and some quantum mechanics stuff. What the hell?